Swayam Prabha. Digital India. Educated India.
Good morning. Today let us discuss about the polymerization techniques, which is in a heterogeneous system. Heterogeneous system means it is heterogeneous from the very beginning. In case of bulk polymerization, you have seen it is homogeneous. In case of solution polymerization, you have seen it is homogeneous system. And this heterogeneous system means the monomer and the polymer both are insoluble in the polymerization medium. In order to overcome the problems encountered during the synthesis of polymerization by bulk technique or solution technique, even in both of those cases there are problems. So, in order to overcome those problems, the suspension polymerization or emulsion polymerization techniques are followed, which are heterogeneous in nature from the very beginning of polymerization, because the monomer which is taken here, the monomer is not soluble in the polymerization medium. That means, from the term suspension, you see suspension, the monomer is kept suspended in a dispersion medium. Here the dispersion medium is water. So, our monomers are organic in nature, hydrophobic in nature. So, hydrophobic monomer, when it is suspended or dispersed in an aqueous phase and it is allowed to polymerize by periodical chain polymerization principle, we get the suspension polymer by the suspension polymerization technique. That means, in a container you take water as the dispersion medium, there you add the monomer, being hydrophobic in nature, organic in nature, it will not be miscible with the water phase. So, it will form a different organic phase, and if it is kept under agitation with the help of a stirrer, so it will form droplets, organic monomer droplets dispersed in this medium. Okay. And here the initiator is taken as oil or monomer soluble initiator. You know, this is a case of addition chain polymerization. Here we need monomer and initiator. Okay. In case of bulk polymerization, you saw that there was no solvent, no other thing, no dispersion medium, nothing. There, if you add monomer initiator to the monomer, it gets dissolved. Then by thermal your decomposition of the initiator, it starts polymerization and polymer growth occurs, and we get the polymer. And in case of solution also, where the monomer is soluble in the solvent, there also initiator is also soluble in the polymerization phase, solution phase. In case of suspension polymerization, since monomer is organic in nature, it is actually kept suspended by agitation or stirring. So, we will find that these monomers form droplet, it remains suspended within the medium. So, here in this case, in order to carry out the polymerization, it is expected that the initiator should be present in the monomer phase, that means within the droplet. That is why it is written oil or monomer soluble initiators. Same benzoyl peroxide as initiator, if you take here, you take water, add monomer, okay, it will form a different layer, then you start agitation. So, that layer will be broken to form droplets. So, some suspension of monomer droplets will be there in the aqueous medium. Then you add the initiator, and since initiator is also an organic compound, it will go to the monomer phase. That means, it will remain dissolved in the monomer droplets. Okay. So, each droplet can be considered as a tiny bulk polymerization system. We do not have any problem to accept this hypothesis. Monomer remains dissolved in the suspended monomer droplet. Clear? Monomer remains soluble in the suspended monomer droplet, not in the water phase. So, here are two phases, organic phase which is suspended or dispersed in the form of small droplet, where the droplet size is bigger than 10 to the power minus 4 centimeter. The droplet size of the monomer is bigger than 10 to the power minus 4 centimeter. If you add the oil soluble initiator, that initiator will go to the monomer droplet. So, it will be dissolved in the monomer droplet, because that initiator is not soluble in the aqueous phase. So, is it clear now? Okay. So, each and every droplet, suppose I am showing it in a separate way, this is the monomer droplet, it contains the initiator. Now, if this system is heated to decompose the initiator, that means, if the initiator achieves the decomposition temperature, initiator will decompose to form free radicals. Surrounding this free radical, there are monomer within the droplet. So, that will gradually convert this monomer droplet to polymer particle. A polymer bead. Any problem? Polymer bead, polymer particle. This same monomer droplet. So, I am showing this monomer droplet in a bigger dimension. So, it contains initiator, initiator decomposes. So, so long the monomer is present over there, this initiator molecules of initiator present within this monomer droplet, that will be converted to polymer, solid polymer particle. So, initially it is actually a liquid droplet, that liquid droplet will be converted to solid polymer particle by this initiator present over there. Since it looks like bead, it is called bead polymerization, because the suspended monomer droplet is converted to polymer particle, polymer bead, like spherical polymer beads, or it looks like pearls. That is why it is called pearl polymerization. Now, here the advantage is, I told that each and every monomer droplet behaves like a tiny bulk polymerization system. So, we are getting the advantage of bulk polymerization system in a miniaturized version. So, the amount of heat generated within this small droplet, that will be dissipated through this aqueous phase. Okay. So, water will take out the heat since it is under agitation, and if this system is in a thermostatic bath or in a attached to a or fitted with a system for heat transfer through this wall. So, heat will be removed, and the problem of that auto acceleration, runaway reactions are all those are avoided. Now, one question comes, how we can keep these monomer droplets suspended. So, for that we should need a suspension stabilizer. That means, if you stop the agitation, or if the agitation is not adequate enough, then what will happen? It will not form smaller droplets. Once it forms smaller droplets, if those droplets are surrounded by something which will prevent the coalescence of merging of individual droplets to again to form a layer, then it will maintain the suspension of the droplets within the aqueous phase. So, and then after supplying heat, it will all the droplets will start polymerization inside the droplet by this initiator. So, all the droplets will be converted to polymerization. So, we can carry out the 100% polymerization here. There is no limit of polymerization up to say 30%, 70%, 80% like that. So, we can carry out up to 100% polymerization, because the heat transfer problem is not there. Here the heat is transferred from the monomer droplet to the aqueous phase and from the aqueous phase to the cooling system. So, it can provide better control of polymerization. We can get 100% conversion in one your batch in one time. So, entire monomer can be converted to polymer with minimum or no residual monomer present within this system. Do you understand? So, whatever monomer is taken within the reactor, that monomer can be entirely converted to polymer, and since it gives proper or and better control. So, we can have a better control over molecular weight, we can have a better control of over molecular distribution, we can have better control over microstructure of the polymer which has been formed within these beads, all right. But there is also again a problem, each and every system has some merits and demerits. So, demerits of this process is that after these polymer particles are formed, it is to be filtered, washed and dried, etc. That is not a problem again, but the product which will be obtained from this thing or polymer particles or beads or pearls like pearl like polymer beads which are available, which will be obtained from this process. So, that will be contaminated by these suspension stabilizers and other things, okay, that may remain with that thing. So, it is a contaminated polymer. So, purest form or pure form of polymer may not be available from this thing, because yes, it is possible, but it has to pass through stringent purification steps, so that the impurities are removed. These suspension stabilizers and other additives which are used during this polymerization. So, those can be removed by purification, but that will incur higher cost. Anyway, still then suspension polymerization is a good process. Say polyvinyl chloride PVC powder. PVC powder, this PVC powder is made by this suspension polymerization process. Polyvinyl chloride powder made by this suspension polymerization process. Now, you are referred to consult a book. This book, Plastic Materials by Bridson. There you can see details of manufacture or polymerization techniques, this suspension polymerization technique there with some sketch of your reactors also there you can see. Okay. So, please go through this book. So, here you see these are the characteristics shown, these are the characteristics shown over here. Ready control of heat of polymerization, as I have already said. Suspension of resulting granular polymer may be directly usable. That means, sometimes suspension can be directly used, or if it is filtered, we can get particles isolated, washed and dried. Continuous agitation is required, less polymer purity, contamination by stabilizer, washing, drying, etc. are required. Now, look at the recipes for suspension polymerization in general. So, these are the ingredients are monomer, water, initiator, stabilizer. This is suspension stabilizer. You know, initiators are peroxides, azocompounds, and stabilizers are carboxymethyl cellulose CMC, carboxymethyl cellulose, PVA, polyvinyl alcohol, carboxymethyl cellulose, this is water soluble, polyvinyl alcohol water soluble, gelatin is a polymer obtained from animals. So, this is also water soluble. So, these polymers actually helps stabilization of the suspended droplets in aqueous phase.
So, what is CLC?
Carboxymethyl cellulose. Carboxymethyl cellulose. PVA, polyvinyl alcohol. Again, here is a science. If you are interested, you can think of science means you see suspension of organic phase, organic droplet, suspension of organic droplet in aqueous phase. So, there is an interface of hydrophobic and hydrophilic. Hydrophilic interface is there, but that is always unstable because of this energy, surface energy. Okay. Now, that can be stabilized if at the interface there is a component which is having both hydrophobic and hydrophilic to satisfy the both of the interfaces. So, this is the, suppose this is a droplet, this is a surface is hydrophobic, and outside is outside environment is hydrophilic. So, here if some layer is present over this hydrophobic surface, this is you can say an amphiphilic component. What is amphiphilic? Having both hydrophilic and hydrophobic. So, towards hydrophobic, that hydrophobic side will be oriented, and towards hydrophilic side of this amphiphilic component will be there. So, these are actually nothing but this CMC, PVA, gelatin, these are amphiphilic components. PVA, what is PVA? So, this is hydrophobic, this is hydrophilic, like this. Okay. So, this way these stabilize the suspension, even if there is some alteration in agitation speed, the suspension will not coalesce, it will remain stable. That is the beauty of this technique.
Sir, once again hydrophobic and hydrophilic.
It is amphiphilic, hydrophobic and hydrophilic. Hydrophobic means water repelling, hydrophilic means water attracting, water your friendly, water friendly, hydrophilic, water repelling, hydrophobic. Phobia, you know the meaning of phobia? Yeah. Phobia, you have phobia on me, not philic, phobic. You are phobic to me, I am philic to you. Here is the problem. Okay. Another recipe for suspension polymerization, please put your attention. Recipes for suspension polymerization for methyl methacrylate, vinyl chloride, very simple. The your composition or the recipe, you know what is called recipe, ingredients and their amounts of a system. Say a food menu, for a food menu, on particular menu there is a recipe, means you have to take some your some carbohydrates, some proteins, some sugars, some salt, and some paper, something like that. So, these are the ingredients, and the total ingredients and the components, total mixture is the recipe. If you do know the recipe, you can cook a good menu, provided you know the conditions and your workmanship. Good. So, here peroxide initiator, water stabilizers, these are the monomers. So, look at these amounts, say more than 180 to 200 parts of water is used for say 100 parts of monomer. If you take 100 parts of monomer, say 100 gram of monomer, so you have to take minimum 180 to 200 or 250 or 300 parts of water. There you suspend at the initiator, that will go to the monomer phase, not in the, that will not remain in the aqueous phase, and it will form a polymer. There is just simplest technique. Then this is most important, emulsion polymerization technique. Majority of the polymers are today are manufactured by emulsion polymerization technique, because this emulsion polymerization can be carried out at lower temperature and lower temperature, as well as the polymerization, the control over polymerization kinetics are better than the other polymerization techniques, emulsion polymerization technique. Can you tell me example of one emulsion? Milk. Emulsion of milk is an emulsion of fats and proteins. Okay. Can you tell me one naturally occurring emulsion?
Bile acid emulsify the fats in digestive system.
Other than biomedical system?
Natural rubber latex.
Natural rubber latex. Produced by? What is the name of the plant? Hevea brasiliensis. Hevea brasiliensis. So, that emulsion means latex is produced by nature, by natural biosynthesis of high molecular weight cis polyisoprene that remains dispersed in aqueous phase, water phase, along with some proteins, lipids, carbohydrates and other sugars, soluble sugars. Okay. That is stable emulsion, but when it comes in contact with air, what happens? It starts coagulation and degradation by bacterial attack. Once bacteria attacks occurs over there, so it becomes acidic. So, that takes it to acidic pH below 7 gradually, and ultimately it coagulates. That is why immediately after this latex is taken out from the Hevea tree, it is stabilized by ammonia and the pH is kept above 7 in the alkaline range. So, these latex or the emulsions are stable in alkaline pH. And what is emulsion? Emulsion is, again you can say, is a fine dispersion of some component in a medium known as dispersion medium or continuous phase, and the size of the dispersions there are smaller than that found in suspension polymerization. That means, this is smaller than 10 to the power minus 4 centimeter. Bigger than 10 to the power minus 4 centimeter, it forms suspension. Smaller than 10 to the power minus 4 centimeter, it forms emulsion. Here also the same problem of stabilization of the emulsified droplets or emulsified particles in a dispersion medium is present. That problem is present. That means, once you stop the agitation, it will separate into two phases, organic phase and aqueous phase. So, when we put some oil in water, what happens? It forms a layer. If you stir it or shake it, agitate it, what happens? It forms an emulsion. You put some vegetable oil in water, shake vigorously this way, shake vigorously, what happens? It becomes whitish, milky like. Why? That oil droplets breaks into smaller droplets, bigger droplets breaks into smaller droplets, and it looks like, since there is some interface created, hydrophobic and hydrophilic interface created, actually that shows this kind of optical property. So, whitish in nature, all right. Now, that is to be stabilized. How it is stabilized? In case of suspension polymerization, stabilization was done by adding suspension stabilizer. What are those stabilizers? Carboxymethyl cellulose, polyvinyl alcohol, gelatin, that means some water soluble ingredients which are having little hydrophobic character and hydrophilic character. So, that stabilizes one suspended droplet from coalescence with another droplet surrounding it or close to it, at the vicinity of it. Okay. Right. Here just you can also, if you extend this suspension system, only the size is small enough, you can call it an emulsion, and these droplets are also stabilized here. Here also these droplets are stabilized. How those are stabilized? Definitely there must be some stabilizers. Now, you have seen, if you put some soap in water and stir it, try to dissolve it and stir it, okay, what happens? That soap solution looks like milky. Why it looks like milky? Because it forms certain emulsions. So, what are these soaps? Soaps, what are the configuration, what are the molecular nature and their configurations of these soaps? Soaps are nothing but some molecules having a polar side, polar head and non-polar tail. Okay. Polar head and non-polar tail is soap, say soap of some fatty acid, sodium salt of some fatty acid, that is soap. Because how soaps are made? Fatty acids are taken from vegetable oils, okay. Those are saponified by adding caustic alkali. So, the soaps are formed. Now, when you add these soaps to water, what happens? It forms, it shows a milky suspension or something like that, because they form some aggregates of these soap molecules with certain geometry, with some defined geometry. They are called micelles. Micelles are formed. What are those micelles? Say, if you add soap molecules to water, it can form aggregates like this, as I am drawing. These are fatty acid, sodium salts of fatty acid, suppose, or sulfonates, organic sulfonates or detergents. These molecules can form aggregates like this geometry, or it can also form geometries like this. So, this is spherical aggregates, this is rod like aggregates, these are called micelles. So, in case of emulsion polymerization, what we actually do? We add this monomer in aqueous phase. Monomers are organic in nature. So, organic phase, you want to disperse that organic phase in water. How it can be done? By agitation. With the help of mechanical stirring, mechanical agitation, we can break that organic layer into smaller droplets or fine droplets in aqueous phase. But you stop the agitation, it will again coalesce to form it will separate into two layers, organic layer and aqueous layer, right. Now, once you break these layers into finer dispersion of organic droplets in water, and if you can stabilize them, then that will remain, as you have seen in case of milk. How milk is coagulated? We add some acid or salt. If you put some salt in milk, milk is coagulated. If you put some acid, we deliberately put some acid for getting, what is that called? What we get after coagulation of milk? Curd. What is called? Okay, find out. Rasgulla. Rasgulla is not directly obtained from your paneer. There is another name other than paneer. He is little clever, bypassing the actual term. Anyway, so why it actually coagulates? That means, if these salts or acids are added, the charge over the emulsified particle is actually neutralized by some ionic exchange or electrolytic effect, then it coagulates, organic phase coagulates there. Now, we are going to study this emulsion polymerization system. Here also what we do? We add monomer in water. Water is the dispersion medium or dispersion medium. In that dispersion medium, we put monomer, that is organic in nature. In order to stabilize the monomer droplets formed by mechanical agitation, we add soap molecules. Now, when we add soap molecules, those soap molecules will form the spherical aggregates. This is the hydrophobic side, hydrophobic tail and hydrophilic head. Say oils are triglycerides of fatty acids, okay, or you take a fatty alcohol, or you take a fatty acid. Now, this fatty alcohol can be reacted with some phosphoric acid, or it can be reacted with some alkali, say sodium hydroxide. Both of them will form, this will form some phosphate ester and this will form some sodium salt. Okay. So, this part ester part will form this polar head, here this salt part will form the polar head in case of this fatty acid soap. So, these are used for forming micelles here, aggregates, either in the spherical form or in rod like form, or both can be present in the system. What happens, since this is hydrophilic zone, core is hydrophobic. So, here this monomer monomer phase can reside comfortably. If there is another micelle close to this, if there is another micelle, the hydrophobic surface, a hydrophilic surface, inside there is a core, there monomer is there. So, this monomer cannot come closer because of the presence of these lipids, lipid molecules. These are actually lipid like, these micelles or soaps are called lipid like molecules or lipids. If sometimes lipids can also be directly taken. So, these are the, so these two cannot coalesce because this is polar, this is polar. Inside the core there is monomer. So, this is a system. Now, you want to polymerize this monomer trapped inside this micelle. For this we need initiator molecule. In case of suspension polymerization, we deliberately added some initiator like benzoyl peroxide, azobis, isobutyryl nitrile, all these things, or cumin hydroperoxide or dicubyl peroxide, these things. So, those gets soluble in the monomer phase in the suspension polymerization. So, there suspended monomer droplet is converted to a polymer particle. Here what is the kind of monomer initiator we can use? If we add benzoyl peroxide or IBN, this emulsion polymerization cannot be done. For that we need water soluble free radical initiator. Can you tell me one example of a water soluble free radical initiator? Okay. Anything more? Anything else? Water soluble initiator? You are doing research in polymer and you do not know. Ammonium persulfate. Okay, ammonium persulfate. Redox system, redox initiator. Who can say redox initiator? As if you are falling from heaven. You are falling from heaven. Redox initiator, example of redox initiator. Who can say? Have you not seen this system? Did I not show you? Did I not show you? Ferrous sulfate, hydrogen peroxide, or potassium persulfate, K2S2 O 7 8. So, potassium persulfate, hydrogen peroxide, ferrous sulfate. So, these are redox initiators. Redox initiators are soluble in water. So, in case of this emulsion polymerization technique, you have to select a suitable water soluble initiator. Then water soluble initiator will remain present in the aqueous phase, monomer in the within the micelle, and that gives you emulsion polymerization or polymer by emulsion polymerization technique. there is resin, there is resin. So, you have already read what is shown over here, components of emulsion system, water as dispersion medium. In the dispersion medium, it contains water soluble free radical initiator, it contains soap micelles in aqueous phase, soap molecules in the form of micelles in the aqueous phase, monomer molecules in aqueous phase also. That means, some soap molecules will remain soluble in the aqueous phase other than micellar aggregates. Now, let us concentrate our attention to an emulsion polymerization system. Let us assume that it contains a spherical micelle, or you can assume a rod like micelle also. Of course, the distance between or the dimension of this core, that is also defined, that can also be defined by, or the space between a rod like micelle, the core space between the rod like micelle, micelle aggregates, those are also fixed. You look at the book, there the dimensions are given 50 angstrom, 50 to 60 angstroms, length of the rod might be 100 angstrom, diameter of the micelle may be 100 to 150 angstrom. So, those things are written there, you take it from book. Now, in an emulsion polymerization system, first some soap molecules are added to water, then agitation is started. Okay. What happens? Soap will be dissolved and some soap molecules will form aggregates and some soap molecules will remain in the aqueous phase. Suppose this is the system, a container is present. The soap molecules are there randomly, this dissolved soap molecules. Okay. And that means, if the concentration of the soap passes a critical level, then only it will form micelles. If you add small quantity of soap, that will be dissolved like this. If the concentration exceeds certain critical concentration, then only the soap molecules will form micelles, that is called CMC, critical micellar concentration, critical micellar concentration. So, we have to take the amount of soap in such a quantity, so that it forms large number of micelles of such kind. Do you understand? Then we add monomer, or we can add both these monomer and emulsifier molecules or soap molecules simultaneously. What will happen? As soon as you add the monomer and the soap micelles and start the agitation, then fine droplets of monomer will be formed and eventually those monomer droplets will be enveloped, covered by these soap molecules like this. So, we can assume that inside this micelle there is monomer molecules present. So, this is a monomer containing micelle. Now, there can be some micelles which may not contain any monomer, simple soap micelles may be there, if the concentration of the soap molecules are beyond this CMC. So, in this polymerization system, what we have added? We have added soap and or detergent and monomer, and some quantity of monomer, some very small although, will remain in the aqueous phase. Suppose this is monomer, I am writing this way, these are the I should use other color. Suppose these are the monomer molecules, some monomer molecules, because although we say the monomers are hydrophobic, organic, but they have certain limited solubility. That solubility may be 1% or less than 1%, or it can be more than 1% also, 2 to 3% or 4% solubility of monomer in aqueous phase. So, after adding monomer to this thing, we will get monomer in two phases, in the organic phase here within the micelle, and in the aqueous phase in dissolved condition. Understand? Then what we add? We add the initiator molecules, because initiators are water soluble. Suppose we add hydrogen peroxide and ferrous sulphate or potassium persulphate, K2S2O8, potassium persulphate. So, there will be some initiator molecules that remains dissolved in this system. Okay. Since this is a redox system, what happens? These redox initiators can decompose at ambient temperature or lower than ambient temperature. It can produce free radicals at 5 to 10 degree Celsius, as well as it can produce radicals at 30 to 50 degree Celsius temperature also. Whereas, if you take benzoyl peroxide or AIBN, you have to heat beyond 50-60 degree Celsius temperature, otherwise those will not produce free radicals. But these water soluble or redox initiators, that can produce free radicals at lower than the peroxide initiators, lower temperature than your the decomposition temperature of peroxide initiators. Okay. So, what is happening there is very interesting. So, these initiators molecules, say hydrogen peroxide ferrous sulphate, that will form OH free radical. You know that reaction, hydrogen peroxide ferrous sulphate reacts to form OH ion and OH free radical, and it becomes ferric, ferrous become ferric. So, ferrous is converted to ferric and hydrogen peroxide is converted to one, say OH radical or as well as OH ion, radical ion. Now, this OH radical being tiny in size, what it does? It enters this core where the monomer is available, where the monomer is there, as well as it is also present here. So, whatever free radicals produced in the aqueous phase, it also contains some dissolved monomer that can initiate this monomer, which are the monomers? Red color. So, this green dot can initiate this monomer. Once it initiates the monomer, some polymer is initiated in the aqueous phase. Try to understand. Some polymer is formed in the aqueous phase, polymerization is initiated in the aqueous phase. Gradually, it will attract more and more monomer, or it will interact with more and more monomer. So, it will continue propagation step. Through the propagation step, that growing chain radical will grow in bigger and bigger and bigger. As it grows bigger, what happens? It becomes hydrophobic. Once it becomes hydrophobic, due to growth of this free radical, size, what will happen? It will try to phase out, come out of the aqueous phase. Eventually, soap molecules are there like friends, they will cover it. So, what will happen? We consider that I have to show that thing in other way. So, here it is being polymerized. So, what happens? Polymer chain is grown, getting bigger and bigger. Eventually, what happens? This will be stabilized by soap molecules, covered by, enveloped by soap molecules. So, this polymer radical is stabilized by soap molecules. Where from these soap molecules will come? These are present in the aqueous phase. So, soap molecules from the aqueous phase will come and cover it. Now, still it is growing. So long the monomer is available within this core. How this monomer will be available? Because in the aqueous phase there is monomer. So, this monomer by diffusion process that will penetrate, that will go inside this system and it will continue. How long it will continue? It has to be terminated. It is to terminate. It will not terminate until and unless another free radical enters there. Now, you see there is diffusion of so many, all the components present in the system, very interesting. So, soap molecules are there, it is covering monomer molecules in the aqueous phase, so that will go inside, and also free radicals are there in the aqueous phase. So, one time can reach when another free radical enters and termination will occur over there. What we are getting? One polymer particle of only one, constituted by one molecule only. And since it is covered by this growing chain is covered by, growing free radical chain is covered by the soap micelle, the probability of entering free radicals, many free radicals inside or another growing chain radical inside this thing becomes less. So, unwanted side reactions of transfer to polymer chain, transfer to initiator, transfer to monomer, transfer to other things becomes less. So, what happens? We can get highest or longest polymer chain or highest molecular weight, and since there is minimum disturbance here, we can get the highest rate of polymerization. So, this is the beauty of emulsion polymerization technique, which can provide highest molecular weight and highest polymerization rate, highest molecular weight and highest polymerization rate emulsion polymerization system. So, this is, I have shown only one representative isolated case from initiation to termination. I repeat once again, in the aqueous phase there is monomer, in the aqueous phase there is initiator, all right. In the aqueous phase itself, initiator decomposes forming free radical and it get access to monomer. So, initiation occurs in the aqueous phase. Once initiation occurs in the aqueous phase, by diffusion process monomer will rush to that initiated monomer site, then it continues adding on to the initiated monomer, that means starting propagation, chain propagation, forming bigger and bigger size of the polymer free radical. As it a time will come when it becomes hydrophobic, sufficiently hydrophobic, we will try to phase out, precipitate out of the system. Eventually, the soap molecules are present in the aqueous phase that will cover it, envelop it like micelle, and that will be stabilized. So, we can write this is micelle stabilized polymer particle. Yes, you had some question.
Sir, at a particular concentration of the soap, the micelle formed by that soap is having a definite size, sir. So can we say that this process gives the polymers of equal chain length?
Although I showed that the monomer is stabilized by micelle, here in this system we can consider this way, there is a monomer reservoir in polymerization plant. What we see, silos, reservoirs, where contains the reservoirs contain raw materials, monomer, catalyst, stabilizer, everything, and from those reservoir or silos, those raw materials are transported to the polymerization reactor. In the reactor, all those components are mixed and react to form polymer. After the polymer is formed, that is transferred from the reactor to the purifications unit. Then polymer is purified, washed, dried, etc., and we get the final polymer in the form of particle or in the form of sheet, etc. Here the monomer is present in the monomer reservoir and micelles are present in aggregates, your soap molecules are present in the aggregates, and if we consider that this polymerization occurs in the aqueous phase. So, initiation starts in the aqueous phase. So, there are so many sites or loci, locus, loci, plural of locus. There may be so many loci where this polymerization can initiate and so many polymer particle can grow simultaneously. Here I have shown only one particle formation, one polymer particle formation. Here is another particle formation can go simultaneously, another particle formation goes simultaneously, another particle can form simultaneously. So, within the system large number of particles, polymer molecules can start formation simultaneously. Thank you.